Now we're going to talk about net force equations. This is what everything has been leading up to. We're going to start to put together all of the pieces that we've been working on. We're going to only, however, look at one-dimensional net force equations for right now. So when we went through the different kinds of forces, some of the forces had specific equations that went with them. So if you have your formula chart, these four forces are the equations that we need for net force equations. The first one is our general version of Newton's second law. And this is what it looks like on the formula chart. But as we write net force equations, we usually use this version. And this time we put our little subscripts to remind us whether we are doing a horizontal net force equation or a vertical net force equation. We have to do separate net force equations for each axis. Now, of the forces that have specific equations, these were the three. The only one we're going to be dealing with right now is the last one, the gravitational force, but I just want to go through them quickly. So on the formula chart, this is what static or kinetic friction looks like. But we usually write it like this, and we sometimes call it the fun equation just because that's what it looks like. Then we have the spring force, and this is what it looks like. It's also sometimes called Hooke's law, and usually written in this form. The gravitational force is written on your formula chart like this, and the reason is because little g is our acceleration due to gravity, but it's also sometimes called the gravitational field equation. Don't worry about exactly what that means right now, but you might see it written that way, and so that's why it's often written in this form. But what we are going to use is when we rearrange it like this. Now, this is also called the weight equation because the gravitational force and weight are the same. So the weight equation is an object's mass times the acceleration due to gravity, and this is our 10 meters per second squared. So what is a net force equation? It's an equation that is written specific to the forces on an object. We build it from our free body diagrams and use that Newton's second law equation. To write our net force equations, we have 9 steps here. But just know, as you get practice and get used to it, these steps come much, much faster. So the first thing we want to know is this a first law problem or a second law problem? What you're looking for are at rest, not moving, constant velocity. Those words tell you that it's a first law problem. Speeding up, slowing down, changing velocity. All of those tell you that we have a second law problem. Next, you need to draw a picture and create an application of force diagram. From there, we do our free body diagram. You have to choose your positive and negative directions, and you need to determine the direction of acceleration if there is any. If the net force is 0, then you don't worry about it. You need to list what you know and what you're looking for. Then we're going to use this as our framework to build our net force equation, and that is going to come from our free body diagram. Then we're going to substitute any of those force-specific equations, in this case specifically Fg equals mg. Then we manipulate the equation for the variable we're looking for, substitute our values, solve for our answer, and then write your answer with units. So let's go straight into some examples. We have a 2,000 kilogram elevator that is accelerating upward at a constant velocity. Before I even go on, constant velocity, you always underline it, circle it, and immediately write net force equals 0. So this is a Newton's first law problem. No matter what happens, constant velocity means net force is 0. So it's moving at a constant velocity of 2 meters per second. We want to know what is the tension in the cable pulling the elevator upward. So we have an elevator. It's a box with a cable pulling on it. If I want to do my application of force diagram, here's my circle. The only contact with the outside world is this tension cable. So I have one contact force, and that's tension in the upward direction. I have the weight force pulling down. That's our non-contact force. So now I'm going to do my net force equation. In this case, I know my acceleration is equal to 0. My velocity is in the upward direction. So my net force equation, my free body diagram is going to have tension and the weight force are going to be same size because they are in equilibrium, and my acceleration is 0. I'm going to choose up as my positive direction, down as my negative, and that is going to be common in most of these. You're going to have up positive, down negative. My knowns, well, I know my mass is 2,000 kilograms. I know we have a velocity of 2 meters per second. And of course, g is a known, it's a constant, 10 meters per second squared. And I am looking for tension. So there's what I know and what I'm looking for. Now I'm going to start with my Newton's second law equation, but written for equilibrium. That is, my net force is equal to 0. Now this is still using our second law equation, but since acceleration is 0, this whole thing is 0. So all of our forces have to add up to 0. We are specifically looking at our y-axis, everything that is vertical. So I'm going to write down what forces are going to be adding up to 0. So all of my forces in the y direction. My tension is pointing in the positive direction. So tension is positive. My weight force or gravitational force is pointing in the negative direction. So I write it down as a negative force. So my tension and my weight force have to add to 0. So now I'm going to substitute my specific forces. Remember, the weight force is equal to mg, and so I'm going to take this mg and I'm going to substitute it in instead of f sub g. So tension minus mg is equal to 0. Now I'm solving for tension, so I'm going to take the weight force and add it to both sides, or mg. So in this case, my tension is equal to the weight force. So I can plug in my numbers now, 2,000 kilograms times gravity, 10 meters per second squared, and my tension moving at a constant velocity is going to be 20,000 newtons. Now the interesting thing about this is that it doesn't matter that it's moving at a constant velocity. If this were at rest, I would get the same number. It doesn't matter if it's at rest or moving at a constant velocity, the tension is going to equal 20,000 newtons. Now the next problem is we have the same 2,000 kilogram elevator, but it's being lowered, so that means our velocity is down to the bottom floor and slowing down. This means we have a second law problem, and it's slowing down at a rate of 1.5 meters per second squared. Again, we want to know what is the tension in the cable of the elevator pulling upward. So we have our box, that's our elevator. Our cable is again pulling up. To do our application of force, that upward cable is pulling up, that's a tension. The weight force is down. And now I need to know which of these forces is going to be bigger as I do my free body diagram. Which direction is acceleration? Because the net force and acceleration have to be in the same direction. Well, if velocity is down and our object is slowing down, that means velocity and acceleration are in opposite directions. So when I do my free body diagram, the force that is upward, tension, has to be bigger than the force that is downward, our weight force. So if up is positive, down is negative, I expect that my acceleration is going to be positive. So now what do I know? I know my mass is 2,000 kilograms. I know that my acceleration is 1.5 meters per second squared, and again we just decided that's positive. I know g is 10 meters per second squared, and I know I'm looking for tension. So this time, when I start my net force equation, I'm going to start with Newton's second law. The net force is equal to ma. Again, I'm doing everything in the y direction. And so I have my tension in the positive direction. My weight force is pointed in the negative direction. But this time, instead of balancing out and equaling 0, they're going to equal mass times acceleration. So this is my net force equation. Now I'm going to substitute my specific my force-specific equations. Again, for us, it's always going to be this one right now. Now I'm going to solve for tension, so I'm going to add mg to both sides. Now in this case, I can actually factor out the m, and it's m times a plus g. Now I'm going to plug in numbers. So I'm going to have 2,000 kilograms times 11.5 meters per second squared, and that is going to give me 23,000 newtons. Now notice my tension this time is bigger than my tension when it was moving at a constant velocity, or if it had been at rest. And that is because of something called apparent weight. Apparent weight is the weight that you feel, not your actual weight when you are accelerating. If you are traveling in an elevator or riding on a roller coaster, sometimes you feel lighter or heavier depending on how you're actually moving. This is called your apparent weight. It's the weight that you appear to feel, and it is due to the normal force. It's due to how the normal force changes. Apparent weight is equal to the normal force. When you stand on a bathroom scale, we think about the bathroom scale as telling us how much we actually weigh. But it is not telling us how much we weigh. It's telling us how much normal force it has to apply to us to keep us from moving. That's why if you've ever stood on a bathroom scale and you push up a little bit on the counter, you can make it look like you weigh less than you actually do. Or if you pull down underneath, you can make it look like you weigh more than you actually do, because the scale reads the normal force, not your actual weight. So let's try some problems with the apparent weight. So in this case, again, we're going to deal with elevators. We have a 60 kilogram man standing on a bathroom scale in an elevator that is moving up and slowing down. So net force equals ma at a rate of 1 meter per second squared. We want to know what is his apparent weight. That's the normal force. So this time, instead of the elevator with a cable, we have our elevator, we have our scale, and then we have our person standing on the scale. Well, we are interested in what's happening to the person this time. So he's touching the scale, so he has a normal force in the upward direction, and then his weight force down. So which one is bigger? Well, he is moving up, velocity is up, and slowing down, so acceleration is going to be in the opposite direction. So the downward force has to be bigger than the upward force. So up is positive, down is negative. Now again, our acceleration is down, so we are going to expect our acceleration to be negative. So what do we know? We know his mass is 60 kilograms. We know that his acceleration is 1 meter per second squared, and we just said it's negative. G is 10, and we are looking for the normal force. So Newton's second law problem, the sum of the forces equals mass times acceleration. So again, we are looking at the forces that are on the y-axis. So we have the normal force pointed in the positive direction, the weight force pointed in the negative direction, and that's going to equal ma. Substitute mg. We are going to isolate the normal force. We can factor out the m, and now we can plug in numbers. So we have 60 kilograms. Acceleration is -1. Gravity is 10. So we are going to have 60 kilograms times 9 meters per second squared, which is going to give us a normal force of 540 newtons. Now, if he wasn't moving, if he was just standing on the scale and not moving, then the normal force would equal his weight force, which was mg. And so the normal force would equal the 60 kilograms times 10 meters per second squared. His weight, if he's not moving at all, would be 600 newtons. So here, with his apparent weight at only 500, he would feel like he weighs less. His apparent weight is less than his actual weight.